Okay, so in this video we're going to take a look at the control design or compensator design used in the DC machines. So in a previous video we've looked at how to model the armature and field current circuits, or behavior I should say, and we will now look at what we need basically to design compensators in order to track the references that we provide. So I mean, in general, you can say that your control circuit would look something like this, or your overall circuit, I guess, would look something like this. So you would have a source, you would have some type of DC-DC converter, let's say. So this is DC to DC, DC to DC. And the output of this, let's say, is connected to your machine, which is modeled like this, as we know. You would need some type of current sensor, let's say, to sense this current, and this would be your controller. Let's call it CTRL for control. You would provide this with some reference, let's say VA star, and then based on all of these measurements and so on, you would produce some voltage VA, and of course this is, let's say, RA, LA, and E. E being the back EMF. And you can also say that this, let's say, is IA. So this is the way that closed loop control usually works. I mean, you have some, well, in the context of power electronics at least, you have some energy source, you have some converter, you have some output, and you're trying to regulate that based on whatever set points you have and you want to maintain. So the overall control loop we modeled previously, we said that the control loop would look something like this. So you would have, maybe we can scroll down so we have enough more space there. You'll have your current like this, and this is a traditional sort of closed loop system. You'll have your current, you'll have some block here, which will be our compensator. We're going to model our converter with a simple block like this. You'll have the plant model here. So this is the plant transfer function. This is some disturbance, and we'll discuss in a second what that disturbance is, and your feedback, of course. So what is this? This will be here IA star, so that's your current, that reference that you're giving. This is the current that you get at the output. Obviously, feedback requires, or negative feedback, I should say, requires a minus sign there. We can call this compensator here, let's say KA of S. So this is a compensator, because this will be used to control or provide the proper reference to the converter. And this thing we can say is VA star, and this goes to your converter, and we can say that the converter has a gain of approximately 1, and this is your converter. So that's the converter there, and then obviously the output of the converter would be the actual armature voltage VA, and that would then be supplied to your plant or your actual DC machine, which we're modeling by this plant. And one thing I want to add here is perhaps we can add here that you would have K phi, and then here you would have omega m, and this entire term is actually the term E, which is the back EMF, and this is subtracted here. Now the plant itself is modeled based off the differential equation, so this is SLA plus RA. And that's this whole thing you can say is the plant. I guess if you want to be really specific, you can say this thing is the plant here, and that this thing here is the disturbance. But one thing we should note is that this is not a disturbance in the strict sense that you usually have. So it's not a true disturbance, because it actually depends on, in some complex indirect way, depends on the armature current. But since omega m, so the mechanical speed, changes slowly relative to any electrical parameters, you can treat it as a disturbance. So the motor speed or the machine speed will always be much slower than the response in current, and therefore we can treat this as a disturbance relative to the rest of the system. So since this is a DC machine, you can assume, well, before we say you can assume, what do we need to do? We need to track constant references, right? So it's a DC machine, IA will be a DC current. So you need to track DC references, meaning it's a constant reference, and you want to reject slowly varying disturbances, which is this back EMF. And for that purpose, the PI compensator is a good candidate. So we can start with the standard PI function. So Ka of S should be equal to Kp plus Ki of S. Ki over S. And that means you can model all of this, and you can simplify this block diagram into something that looks like this. Before we do that, we should probably go to our feedback. So your control should look something like this. This will go into the plant, and the plant is modeled as follows. So this is 1 over SLA plus RA. And this is your disturbance. Let's just call it E for now, because we know we've seen above how to generate it. So we don't need to keep drawing that over and over again. And this here will be Kp S plus Ki all over S. So the output is obviously fed back. Subtract that. This is IA star. This is IA. So this is the control loop that we have for the armature current, right? So this is for IA. Now, if you want to determine the parameters of the compensator, or the compensator gains, I should say, you have to write the loop gain, right? So let's say loop gain. Now, what's the loop gain? In this case, the loop gain, L of S, is equal to KPS plus Ki over S times 1 over SLA plus RA. Okay, now you can manipulate this and simplify this, and you can get this to look something like Kp over LA times 1 over S times S plus Ki over Kp all over S plus RA over LA. Now what we do here is we do this thing called pole zero cancellation. So you cancel the pole of the plant with the zero of the compensator, meaning you'll be left over with an integrator. And we all know that integrators can track DC references without any issues. So this is a sort of little control trick that you would have learned, I guess, in a introductory control systems class. But we're going over it again here just to make sure everybody's on the same page. So supposing you cancel Ki over Kp with Ra over La, then that would imply that Ki over Kp is equal to Ra over La, which then means that L of S, the loop gain, is equal to Kp over La times 1 over S. So this is an integrator with some gain. And then if we want to write the closed loop transfer function, which is the output, Ia, over the input, which is Ia star of S, we know we can write that by Ls, or L of S, over 1 plus L of S. And if you do this and you simplify this, you'll find that this turns into a function that we're very much familiar with. And this is the 1 over La Kp S plus 1. And the reason I say we're familiar with this is because this is a standard sort of first order function, where this is, we can call this tau A. So we can define La over Kp as being tau A, and that's the time constant, the closed loop time constant, that is. And so this is a first order transfer function with no zero, which is, I guess, about as nice of a transfer function as we can hope for when dealing with this kind of situations. So, practically speaking, what does this mean? This means that if you have a signal, let's say, this is your reference, and you suddenly change the reference to some value like this, you expect that the first order, let's call this reference, you expect that the first order response will do something like this. It'll be 0 for that much time, and then it'll track with this type of first order behavior. And the time constant, you can basically say that the time constant, or the signal tracks the reference in about 4 time constants. 4 tau A, let's say. Now, our job as the designer is that we get to pick, so we can say you choose. So you choose what this time constant should be, and you should choose what this time constant should be based on the application itself. So if you need a fast response, you can set this to be a low time constant. If you can live with a shorter response, or sorry, a longer response, and you don't need a short response, then you can make this a larger number, and you can get away with that. And so we can simplify all of this, and we can say that since tau a is equal to LA over KP, then we're more interested in the gains, obviously. So we can write this expression in terms of the gain, which is LA over tau A. So you decide a value of tau A, and based on your machine parameters, your machine LA, you can determine what the value of KP is. Now, the next equation for the integral gain, or the KI gain, comes from the condition that we imposed. So KI over KP is RA over LA. We said this was true. This is what all of this is based off of. And this implies that KI, sorry, there's no divided by there, KI is equal to RA over tau A. So with these two expressions, you can calculate your compensator gains for the armature. Now, we can do a similar thing, but for the field circuit, right? So the field circuit, if you recall, and we did this in a previous video, and I'll link the control models video in the description below if you're not familiar with how we derive these models. But the field circuit model, and I'll go through this. I'll go straight to the simplified version, assuming a PI compensator, because again, in the previous video we showed how to achieve this this block diagram, and so that would be your compensator there. You have your VF comes out and goes into some. Maybe we can make this larger since the function itself is has a few more variables than the other one did. So this is IF, and of course this is your feedback, like so, and it's a negative feedback, and we can say IF star is here, IF is here, and we say VF is there. Sometimes people like to call this thing the error, so they call it EF, and I suppose at the top we can call it EA if we want to. So this is your compensator. We can say this is KPS plus KI all over S, and this is not the same KP and KI. So be mindful of that. Like, we write KP and KI because we assume these are all in their own context. We usually don't juggle these variables back and forth. So one control loop's variable will seldom be used in another control loop. So, but again, the point of what I'm trying to say is that KP and KI are not the same KP and KI that we determined above. And maybe when I write them, I'll write like phi at the bottom for the field circuit. Anyhow, this transfer function we said was 1 over RF, and then this was tau Fs plus 1. And this is what you need. We also defined, in a previous video, we defined the time constant, tau F. So we said tau F was Kf over K prime RF. Now, one thing you should understand is you don't need to know all of these parameters for the machine. You just need to know this tau F, and you can usually determine this experimentally. So you don't need to go in and have all of these numbers. If you have this, it would be sufficient for control design, although you might need to know these parameters for something else. So what we're going to do is we're going to apply the same pole zero cancellation technique. So we have the loop gain LS is equal to, well, the manipulation looks a little bit different in this case, but we do the exact same thing. We're going to say S plus KI over KP all over S. And then this is 1 over RF tau F divided by S plus 1 over tau F. And so you see there's a 0 here, this is a 0, and this is a pole. And we're going to try to cancel the two. So we're going to force the condition that Ki over Kp is equal to 1 over tau F. And that implies that the loop gain Ls is going to be equal to Kp over Rf tau F times 1 over S. So again, this is a simple integrator, which means we'll be left with a simple first order function for the closed loop. So what does the closed loop transfer function look like? The closed loop transfer function is IF over IF star. So that's the output over the input. And that, if you simplify it, you'll get it's 1 over tau I s plus 1. And we choose tau I again. So if we choose tau I, and again, you would actually write this expression in the same form as I did last time, but because you know what it is and these are trivial steps, I'm skipping them. But if you do this, you'll see that Kp is equal to Rf tau f over tau I, and Ki is equal to Rf over tau I. So again, this is the, maybe we can move it over and we can just write what it is so it doesn't confuse anybody. So this will be Ls over 1 plus Ls, and that's equal to 1 over tau I plus S. And we say that tau I is what we choose, and according to this definition here, you can write whatever tau I is in terms of any one of these things. So these are the expressions that or the calculations, I guess, that we have to perform in order to determine what the compensator gains are. So let's go back and let's do a recap of what we just looked at. So we start off with the idea that we have some DC-DC converter that needs to, this DC-DC converter needs to regulate, well, I missed one really important part, is this actually has to communicate with the converter. So it's not enough to just control, you actually have to send the signals to the converter. So that was a mistake on my part. And these are usually gating pulses, so they'll turn switches on and off inside the converter. But yeah, this is your machine model, this is your converter, and based on your measurements, you can implement some control. What we looked at here is the closed loop control transfer function. You can simplify all of this to look something like this, assuming a PI compensator. And the reason we assume a PI compensator is because we need to track constant references and we need to reject slowly moving disturbances. And for that, a PI compensator is the perfect candidate. So we've done that. We implement that here. We calculate our loop gain in order to determine what the closed loop transfer function is. And then what we can do is we can determine, well, we can set the closed loop time constant of the armature circuit to be whatever we want. Now, I guess we should talk about, well, we can mention that tau I, just to give you a number, I guess. So let's say 2 milliseconds, tau I, sorry, A, 10 milliseconds, usually. So usually this is fast enough, unless you need it to be faster for some reason. But in most cases, for something like this, you can usually get away with something something in the order of this rate. And so this is why, when I was mentioning earlier that the mechanical speed will change at a much slower rate than either of these, and so you can treat it as a disturbance for that reason. And so you can choose any one of these numbers. Based on these, you will get some parameters here, and then you can implement these into whatever programming or simulation or however you're implementing the system. And one thing we should mention here is that the field current doesn't have to be particularly fast. So the reason that is because IF is related to omega m, which is the machine speed, the mechanical speed, and that changes slowly. So the changes in IF will be slow, meaning this can be much slower than this. So let's say you set this to be 10 milliseconds, or let's say you set this to be, let's go in the middle. So 2 and 10 is 6 milliseconds. Let's go 5 because it's a nice round number. So 5 milliseconds, time constant. And you say that this varies very slowly. So what's the time constant of this? Much slower than this, right? So if it's much slower than 2 milliseconds, or sorry, we said 5 milliseconds. So if it's much slower than 5 milliseconds, let's say it's 20 times slower than 5 milliseconds. So 20 times 5 is 100. So then you can set this time constant to be 100 milliseconds, and then you can calculate everything here according to that. So, I mean, there's no correct, I mean, well, there's good and bad ways to design control, but there's no correct, absolute perfect approach. But this is about as good as it gets for all intents and purposes of the kind of stuff we're doing. So, I hope this was helpful. If you have any questions, leave them in the comments below. Like and subscribe to support the channel, and we'll see you in the next one.